Let's talk about a core engineering concept: why some things bend and others just break.
For a lot of materials, the answer is a hidden force, one that causes sliding on the inside. So anytime you push, pull, or twist something, you're creating what we call stress inside it.
We're going to focus on ductile materials, like steel, stuff that deforms before it snaps.
When you pull on a bar, that creates a direct pulling force. We call that normal stress. But here's the twist. For these materials, that direct pulling force isn't the real danger.
The real culprit is an internal sliding force called shear stress. Think of a deck of cards.
And get this shear stress is actually at its max on a 45-degree angle to the pull.
Basically, for ductile materials, it's that slippage from shear stress that causes them to yield.
And that brings us to the main idea, the maximum shear stress theory, or Tresca's criterion.
So what Tresca's theory does is bridge the gap between simple lab tests and the real world.
But in a real part, with all kinds of forces, how do you find that maximum shear stress? Okay, so any single point in a material can have both normal and shear stresses acting on it.
Well, engineers have a really elegant tool for this. It's a graphical method called Moore's circle.
You plot the stresses you know, and they form a circle. The circle represents every possible stress state.
And the best part? It's so simple. The maximum shear stress is just the radius of the circle.
Yep, Tmax, the number we've been looking for, is equal to r, the circle's radius.
Now, this is where it gets interesting. Let's see how Tresca's theory stacks up against other models. Tresca's theory is what we call conservative. Its prediction fits inside the others, giving a built-in safety margin. This is absolutely critical for designing things like drive shafts, which get twisted and bent all the time.
So why does this matter? It lets us design parts that safely bend instead of catastrophically failing. So if shear predicts bending, what makes something just snap? Well, that's a whole other story.